So the main thing that makes differentiation with side conditions different than what we've been doing up to this point is, up to this point it has been clear from the context that the independent variables were either x and y, or they're x, y, and z, or they're whatever other silly letters we were using, u and v, or s and t, or theta and beta, whatever. In this context, these kind of problems, the ambiguity, the thing that makes them slightly tricky, is you could have different choices of independent variables. So let me show you a physical example. So do you guys know the ideal gas law? PV equals to nRT. Ever seen this? Pressure times volume is equal to the number times the gas constant times the temperature, right? So here R is a constant. So this is the so-called ideal gas law, all right? And so if we take the total differential of this, we could have, what would we get? Well, we get, like V dP plus P dV. Do you want to, we can take n as a constant, or I'm going to take n as a constant here, if you guys don't mind. It's the number of particles, okay? We'll take it to be constant for the moment. And so this is going to be, nR dt, right? So let's see, we could go a couple different ways here. We could solve for dP is equal to, nR dt minus P dV, all divided by what? V, which I'll clean up. That's nR over V times dt minus P over V dV, right? Or we could solve for dV. And that would give us, nR dt minus V dP divided by, well, P. Clean that up. We have nR over P times dt minus V over P dP. So sometimes in a calculus book, you'll find them ask the question like this. Okay, so what's this? If I take partial P partial T times partial T partial V times partial V partial P, what's that equal to? So I guess I probably should add one more to our list, right? If we solve for dt here, what would we get? I can put it up here. dt is what? V over nR, right? dP plus P over nR dV, right? So let's call this 1. Let me call this one 2. Let me call this one, for the sake of reference, 3. All right, guys. What does this mean? Can we make this more meaningful, is really my question. Whoever wrote this, what have they forgotten to tell you? Right, what are the independent variables for each expression? This is actually a hybrid expression because it's a mixture of worlds. Like every one of these partial derivatives is inside a different context. The first one has to be holding what? So the variables here are P, V, and T. If I'm taking P as the dependent variable, then T must be the independent variable. What's the other independent variable? V, right. So this is holding V constant. This one must be holding P constant. This one must be holding t constant, right? All right, so what is partial p partial t holding v constant? Well, to calculate partial derivatives of p, I look up here at my dp formula, and so like that's nr over v from 2. And then partial t partial v, well, that's up here. That's p over nr, right? That's from 1. My third one, partial v partial p, that's from 3. And that's, actually, before we do this, what do you guys think this works out to? I mean, shouldn't it be 1? Because like the partial p's cancel, the partial t's cancel, the partial v's cancel, right? This should work out to 1, right? So Sir Roger Penrose calls this one of the 2 fundamental confusions of calculus, that this should work out to 1. I'm not sure it really raises to that level, but if he, I mean, I have to, you know, he's a very smart man, so maybe he's right. But it does not work out to 1, actually, because, check this out. Yeah, -1. Ha, indeed. So we have a minus v over p. And so what do you got here? But it just literally simplifies to -1. So, yeah, I mean, this kind of like heuristic canceling partial stuff, sometimes it works, but sometimes it falls flat. This is one of those places where you actually have to work it out. By the way, the fact that this worked out to -1 has almost nothing to do with the ideal gas law. This is a generic thing that will happen if we're working with like 3 variables with 1 equation. Can I erase this? Yeah, okay. By the way, this was example 4.79 in my notes, which is wrong. We fixed it in class today. All right, so like there's some typos there that I need to fix, obviously. So let me like do example 5 just generically, yeah? So example 6, if we're looking at f of x, y, z, you know, equal to 0, let's say, then my, you know, df is f sub x dx plus f sub y dy plus f sub z dz equals to 0. And from this, I get dx is minus fy over fx dy minus fz over fx dz. I get dy is minus f x over fy dx minus fz over fy dz. And I get dz is minus fx over fz dx minus fy over fz dz, solving this equation up here respectively for dx, dy, and dz. So if I calculate partial z partial x times partial x partial y times partial y partial z, what do I get? Oh, yes, thank you. I had part of it right, but I messed up my differential. So like, all right. Respectively then, partial z partial x is holding what? Y fixed, z fixed, x fixed, for that to make sense. And so the z derivative is this guy. The x derivative is this one. Oh, wait a minute. What's that? Did I do it wrong? Where? I'm sorry, I'm.
Give this first partial, partial z, partial x. We look down here, dz, and tell me the x. The first term.
Sorry, I'm not seeing it yet. So what were you saying?
You have to trace down the partial z, partial x. We go down here to the dz, right?
The dz, yeah.
So we take the first, let's say it's partial x.
Oh, the xz.
Yeah.
Oh, I'm sorry. Dumb. My bad. Oh, so yes, I'm an idiot. This one. Thank you.
Yeah.
Duh. It's because we're calculating the partial derivative with respect to x. So that one, right? Then that one is, this one's correct, minus fy. And I knew as soon as I wrote it, I knew it was wrong because there should be like a cancellation of things. And then the third one here, partial y, partial z, this guy. So we've got minus fz over fy. And you see what happens? As long as they're all non-zero, right? Notice this. This calculation only makes sense in as much as all of the partial derivatives are non-zero. There's a deeper truth to be understood here, which is those partial derivatives, non-zero, speak to the possibility of solving for that one variable in terms of the remaining two. Like this is actually the criteria. If I want to solve for z as a function of x and y locally, I actually need that fz is non-zero. Otherwise, I can't solve for z as a dependent variable of x and y. Likewise, if I want to solve for y in terms of x and z, I actually need that this fy derivative is non-zero. Otherwise, I can't actually solve for y locally. And likewise, if I want to solve for x, I need that f sub x is non-zero in order to solve for x as a dependent, as x depending on y and z locally. This is what I'm sharing with you guys is known as the implicit function theorem, which I got more to say about next class. But as you can see, this is minus 1. Anyway, I do have more to tell you about differentiation side conditions, but that's all I got for today. So thanks, guys.